All right, so how are you guys doing today? Doing good? Okay, perfect. So let's try to finish up the chapter today, hopefully today. So the last time we talked about the nucleophilic, aromatic uh, substitution. So the once again, like I said before, I'm not gonna do this much because it is very rare, not so common, relatively speaking to the ones we did quite a lot with the electrophilic. But we'll just do this one, and then we can just move on. Okay. So if you have the halogen groups with the electron withdrawing groups either on your ortho or para position. So for example, you can put the natural group here. Let's try to make it. So if that is the case, if you have some type of base with a certain degree of temperature, you may have the nucleophilic substitution, not the electrophilic. So what happens to this one here? So I briefly explained last time, but this goes to this position. Then that obviously will make this negative charge on here. So then this will push the pair of electron in this double bond to here. Okay? So that makes the carbanium form on here, and then that makes the double bond to the nitrogen. So that goes up to, that makes the push one of the pair of electron up here. So it becomes negative. And then it goes down again. And then the double bond was pushed. So yeah, this is the same problem. So so let's do this one by one. So what happens to this one? So let's say we have this one, right? So you have this one. So this is a negative charge, 1, 2, 3, 4, 5. So then it goes to, so this double one will move the charge. Okay, over here, and then that goes to make a double bond on here, which is okay. So then that goes to. So can I just draw this part maybe? So maybe you have this one, and now this to here. This one. Okay. So in that case, now this push back again and push back, and then this goes to. Okay. So in that way, you're gonna replace this one to the hydrogen group. Okay. Do you guys see this? I know it's kind of a lot of steps you need to follow, but this is happening on here. So this is a substitution you can see. When you have something that can take into the electron into their electron withdrawing groups on the ortho position, or para is also possible, because if you look at this one very carefully, once you have this position of the carbanium here, you can also move to this double bond to here. So that makes, and then it goes to the here, right? Because you move to this one here, and then your carbanium will be right underneath of your nitro groups, and the rest of them will do the same. Okay, good there, and top down, 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 and down. Okay, so it doesn't matter if it's on the ortho position or the para position, your Witten groups on your substitution reactions, because of your relocating carbanion on this right under the electron Witten groups, you can have another sequential reaction, the movement of the pair of electron that makes your halogen groups leave. Either you have with electron Witten groups on ortho or para position. Okay, but if you have this group on here, okay, let's think about it. So I'm not going to draw all of that, but if you have this one here, whenever you have attached to the base hydroxy group over here, your carbanion point is here, but if you move to this position, only position you can have is those three, which you can have the carbanion position right under the nitro group here. So it will not happen. So that is why either you have this group or this group would do the nucleophilic substitution, aromatic substitution with the base. Okay. So if I have this one comes in, go replaced by this one eventually. But maybe on the exam, I give you this one, your answer should be no, nothing. But these two will replace your halogen group with the hydroxy group. So if you have a Witten groups, electron Witten groups on the ortho and para position, that's the product. But based on the meta position here, you have nothing happens. Okay, I'll move on because this is only one thing I want you to know for this chapter. But like I said, this is not so common anyway. Okay, can I move on? So yeah, just remember if you have this Witten groups on the meta position, nucleophilic or not. All right, so the next part is benzene. Okay. So benzene looks like this. You have this is benzene, right? But you have a triple bond here, okay, somewhere in your benzene ring. So you have this is like a triple bond, okay. So you have some type of the triple bond inside the benzene ring. So we call this like a benzene because it's the benzene with the triple bonds, okay. So one thing I can show you is this one. Base. Okay, so it will be quite high temperature and so on, but this high temperature, high pressure. So this is I'm going to explain how you're going to use the benzene to make this the reaction here, but what you can do is whenever you have this benzene intermediate, maybe reaction. I'm going to say this is reaction intermediate because can you see this? This will be very unstable, right? You think this is not? Do you have two double bonds over here, triple bonds? I mean, the benzene itself is very well conjugated with double bonds, sp, sp2, sp2, all very well stabilized. But benzene will be very unstable. So in a way, you get this benzene type of the intermediate has to be very happening at very high temperature, high pressure to make it go over the very unstable intermediate. So if that is the case, what you can have is the this one. Okay? This is the some substitution you can have from the benzene structure. I'll explain why, but the obviously you don't have to know for the mechanism for the exam, but you just need to know what makes what. Okay, but make sure you guys have a high temperature, high pressure over here. Okay? So what happens to this one is simply this one. So if you have this one, I don't normally show the hydrogen, it's always implied there. But when it does, okay, the base will take one of the hydrogen over here. Okay, so then this goes to the electrons in here will goes to this one, and then this will make this leaving groups leave quite easily. Okay, so if that happens here, you have this one, okay? Because the end of water, okay? Right, you see that, right? This base comes in, grab this one. So this one will go to on the top of the double bonds. So that's why it becomes a triple bond, right? So then this will leave. So this is okay. And then remember the position here, those two, the carbons in the triple bond. They actually have two equivalent carbon here, and whenever you have water, let me draw it in the. And this position goes to here, okay, and then this one of the paired electron goes on here, okay. And then what happens to this one is. Carbanion form here in this double bond, and there's the water become positive charge, and so you have this one is quite unstable, right? So they wants to put obviously this way because it's electronegative. So then no, then this one becomes a neutral, but that goes to the hydrogen cation. You see the pair of electrons in here goes on the positive oxygen here in water. So this has become neutral, and now it becomes positively charged, and then it grips this one. Okay, so then you eventually see this one here, and this position. So you have this the hydrogen group was added on in this our structure. Okay, does it make sense? You good? Okay. So let's do one more. Okay, let's do one more benzene. Okay. So basically, what it does is you have a very strong base only at the high pressure and temperature, because as you know, benzene is very unstable. Then they actually gonna behave like grab the other groups, and then whenever they have a hydrogen available, they catch it. Let's do one more. Okay. The other one was bromine. Okay, we have other halogenated benzene here, and we have maybe sodium amide with the ammonia. Okay, and then it's pretty much the same. Once again, what it does is as you know, there's a implied hydrogen here, right? And then this one this one will grab your one of the hydrogen right next to your halogen groups, and then they become ammonia, right? This is conjugate base of the ammonia here, so this will grab this one and goes to there. Okay. So then we'll make this one leave. Okay. So then you have also same here. You have a benzene over here, okay? Because of the base, and obviously also at high temperature and high pressure. And then then you have ammonia comes in and try to attack, and thus the one pair of electron goes on here, so it becomes okay. So pretty much the same, right? Just a different base, different groups attached to it. Okay, but we have the same benzene intermediate. So then, as you can see, okay, then you can just go here. So this will break apart. This become neutral. Okay, okay, and then it grips. So eventually you're going to natural group there. Okay. No, not natural. I'm sorry. The main groups, amino groups there. So that makes sense. So yeah, please remember it should be, because the benzene is the characteristic, has to be happening in the high and temperature and pressure. But with a strong base, you can also do this type of reaction. The one thing I want to point out here is the it could be here and so I think yeah, that's the once you have a benzene position here, you can have so. Do you guys see this? Whenever you have the groups onto the this benzene, where you can find the triple bond, they can either do this way. They can either do come here and make it over here, right? But how about we do the other way? Here and here. Okay. So you can have where you have two carbons in the triple bond in the benzene, you can have addition of that group on either here or here, 50% chance. 50%. So for this one, we didn't have much of a problem here, okay? But we have. Does it make sense? So the carbons in the triple bond in benzene, they're equivalent to each other. So either they can attach to here. Carbanium position will be in the opposite carbon. So you can have a 50% on each carbon have addition on the groups. Okay. So it becomes a bit more important whenever you actually have. I'll give you one example here. Yeah. So I'll give you one example here. Here. Okay. So in that case, you're going to have you're gonna grab this one with the base. Okay. So then goes there, right? So then you're going to have this will leave. Okay. So you have this is where you have a benzene position here. Okay. So whenever you have groups here, because of this one, if you don't have this one, it doesn't matter. Either they bound to here or here will be the same compound. But if then is the maybe toluene base, okay, toluene base, then you're predicting either you're gonna have the amino groups here or here, 50-50, right? So in that case, they're going to be two products because of that. Makes sense, right? So this is you're going to have one, and there's another one, and other carbon, and the benzene triple bond position. Okay? Because of that. Okay? you see it now. So you can either attack here or here. So you can make the Calvinian position here or here. Doesn't matter because equivalent teaching. So it'll be 50%, 50%. You're gonna have the two products because of it. Okay. Okay. Make sense, right? We good? Okay. Can I move on? Can I move on? Let's go. Okay. So yeah, pretty much the same. Once again, only thing you have to know for this type of reaction is with the strong base, those are really strong base, what we just discussed. With very high pressure and temperature, even very unstable benzene can be in your reaction intermediate. You can have this type of reaction. And also remember, there will be half and half chance for either position addition of the groups. That is your product. Okay, so the next part. So the next part is oxidation of your alkyl side chain. So this is kind of funny. You actually kind of love it actually. So if you have this one here, obviously you have alkyl groups on the side on the array groups here, which is your aromatic compounds here. If you try to oxidize the compounds, obviously this part is very hard because this is a very stabilized conjugate region where you don't want to do much of a change unless you have very strong like oxidant reducing or other type of catalysts and all very severe case. But in here, it's relatively speaking easier to make change because it's just the alkyl group, right? So if you have do you guys remember this one, right? This is very strong oxidizing agent. Okay. So if you do this one over here, okay, what happens to this one is you have so this is the position we call benzylic position. So any carbon right next to your array groups, which is the benzene ring, that is where we call benzylic position. Okay, so benzylic position here, you're actually going to have that carbon will be oxidized so well it becomes benzoic acid. Always the benzylic position, not here, 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 but just here. Okay, so this is really good example of oxidizing. As you know, this makes really oxidizing your alkyl parts of your compounds. Just making a carboxyl group in whole on your benzylic position of your aromatic compound here. So this is a really good example of oxidation. You see this is very oxidized on this alkyl side of the compounds. For this one, I'm not going to do the mechanism because they'll be too complicated. There are so many steps you need to go through. Can you guys guess why? If you look at the textbook here, they don't even go and try to explain the mechanism because of this one. The permanganate is very complex. They do very complicated numbers of the steps to make the oxidation steps. So sometimes we do have a abbreviation of the oxidation over here. But if you want to know, you can stop by my office. I can explain. But obviously you don't have to know for this one. But the one thing I really want you to know for this one is whenever you have alkyl groups on your compound here, the benzylic position is where you're going to put the carboxyl group there. So that makes benzoic acid there. Okay? But that's all you need to know. Okay? Makes sense, right? It's pretty easy, right? So you have a benzylic position, just any carbon here. You have potassium permanganate. This comes in to make the carboxyl groups, so it becomes benzoic acid. So I think it's pretty straightforward now. Not the mechanism-wise, but if you want to know about the mechanism, you can stop by my office. So anyway, but there's one more thing I want to tell you. If I do this one, it's top butyl benzene. If I do this one here, your answer should be Now. Okay, it's because of the mechanism again. Do you know the permanganate is very bulky groups, bulky anion. So if you have some quite bulky alkyl groups on your aromatic compounds, they will not have a good interactions, good reactions together. So in this case, it will not happen. So that was why I gave you the first, the primary alkyl groups as a good example. Secondary they may do, but the tertiary for sure no way. It's too bulky each other. So there will be no reaction there. So if I put this one on the exam, the oxidation will not happen. That should be your answer, because this is very bulky. Makes sense, right? Okay. Perfect. Good and great. So this is pretty much before. Oh, there's one more oxidation. Let me actually tell you too. So whenever you have two groups on here, you're going to have two position. And we're gonna do NBS, which is nitrobromosuccinimide. Okay, so we have this one. Okay, so in this case, also same. You're just looking at the benzylic position over here, and they're going to substitute one of your hydrogen here. Okay, so there's two hydrogen, 3, 2 here, but only on the benzylic position here, you're going to replace your hydrogen to bromine. That's it. So what happens to this one? Okay. This one. Yeah. Okay. So this is all you need to know. This one is only happening at the benzylic position because this benzylic position have a very high stability. Because of resonance, radical resonance, that would be the better. Okay, so what I mean by that is, as you know, this one here will have okay, let's try to have you have a hemocleavage on this bond here. So you have a radical carbon right here, okay, and you have a radical hydrogen over here. Let's say we have that position has a radical point, and then what they can do is they can do this one, and this one, and this one. So then you can place your radical position to here by just doing this. Okay, so you have it over here, right? And then you can also do this, and this. Oh, sorry. It's always a half-head arrow. It's a fishy hook, okay? Because it's I'm showing the one electron movement for each. So if we have electron moving one here, okay? So then that goes here and here. So the radical position is now here, okay? And then you do the same fish hook, fish hook, fish hook. So your radical position will be here, okay? And you can do the same over here as well, okay? So that makes the radical position like in the kind of resonancing together. Do you see this? That is why the benzylic position is the very stable position where you can have a radical form. In that way, it will replace only the hydrogen on the benzylic position by bromine. Okay? So, does it make sense? Makes sense, right? Because it's the you see the radical resonance there, right? So then okay. So let's say you have a radical point right here, okay, with the hydrogen was also hemocleavage. So then you have this one comes in and make formic acid over here, and then they actually going to onto here, and then goes to here. Okay. Oh, no, sorry. goes to here, goes to here. Okay. So then hydrogen cation and bromine 2 will be there, and then this will grab this one. So this will become catching hydrogen instead of bromine. So you substitute that one, and this breaker part as a radical bromine here, and where you have a radical position here, there, so you have a bromine. Okay, so once again, you don't have to know the mechanism. I'm just doing this for your. It will be easier to look at what is happening, but obviously on the exam. If I do this one with the MBC, N-bromosuccinimide, just make sure you put the bromine on the benzylic position. So if I give you the exam like this one, that'll be wrong, right? Because if I put the bromine in here, it'll be wrong. Because it's not the way you can have a very stable radical resonance position, but it has to be here. So there will be multiple choice. There will be bromine here, 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 here. And then the one on this position is the right answer. It's pretty easy, right? Okay. So just because of the benzylic position, okay? Because of this radical resonance form. Okay. Does it make sense? You good? All right. So all right. So if I give you, for example. If I give you this, okay, there will be some phenolic, benzoic, like some of the radical initiator, but don't worry about it. And then your answer will be this one, okay? Right, just the benzoic position here, and just put the bromine there. Because we don't normally show the implied hydrogen here, right? Because we know there's a 2 hydrogen anyway. So just do this, but okay. All right. So the other one. Okay. So let's do reduction now. Okay. How about we have a reduction? So obviously, the reduction is very hard because especially on this one. You can easily reduce the one in the benzene because this is already very stable. They have to be halogenated, so they want to be reduced. But once again, if you have some alkyl groups right there, and this is what we learned in Orgo 1, right? Either you can do palladium or platinum, doesn't matter. This is your like base. They do halogenate on those 2 alkene, so then you can have here, okay? Because this will be gone, but not this one. This because this is very stable already. But relatively speaking, this is easy to control because it's not so stable anymore. This is very very stable, not so stable. I mean, relatively speaking, so you can reduce only this part, not here. Okay. All right, here's one more thing. Okay, this is quite tricky, so let me try to do this. Okay, so if you have this one over here, you have a double bond in your alkyl groups on the benzene. You also have a carbonyl groups here. So as you know, the carbon this is also Orgo 1 thing, but carbon and the oxygen. The double bond is very strong. So whenever you do the same thing, palladium, if you do this one over here, you actually going to have, so benzene stay the same. Also, the double bond in the benzene stay the same. This will also will stay the same. But this one will be reduced. So just alkene. So it'll be okay. So because of the carbonyl groups and the benzene will not normally go through the reduction much, but this is relatively easier to be reduced. Okay, so we have this one. This is the correct answer. But here's the exception. I'll give you this one. So once again, this is the beauty of the benzylic position again. So whenever you do this one, this will be reduced. This one. Okay. So this will be an exception. So normally the carbonic groups will not be easily reduced, but because of the characteristic of the benzylic position, it can be also reduced with this one. Okay. So if I give you this one, it's still the same. So this is also easily reduced, and this is carbonic group, normally not so reducible, but because of the benzylic position, they can be also reduced. And here, so the answer will be this one. Okay. So does it make sense? So if I do this one, the answer will be this one, because it's not on the benzylic position. But this double bond can be always reduced in alkyl side. But this is not so much. Benzene is always quite stable. They don't want to be used anymore because it's already quite stable anyway. Does it make sense? So you can always reduce the double bond on the alkyl side, but the carbonic group, no, because it's very hard to reduce. But based on the benzylic position, you can. Okay? So does it make sense? Good? All right, does it make sense really? Okay, so can I do one more? So if I do, what's the answer? If you do, what will be the answer? So this is on the carbonic group, but also in the benzylic position will be reduced. Okay, so it will be reduced. And also these two also will be reduced. So that's the answer. But if the carbonic groups are here, will not be reduced. Just the double bond on the alkyl side. Still not on the benzene. Benzene will stay the same because it's very stable. Makes sense, right? So this is a benzylic position reduced. Okay. If it's not, will not be reduced. When the double bond on the alkyl side always reduced. Well, it's very easy to actually reduce. Okay. And then just one more thing. Okay, I'll do one more thing. I'll stop here. So if you have, like I said, benzene usually not reducible, right? I said, oh, it's very hard to reducible. But if you do either platinum with a very, very high pressure, I think it was about 150 atmosphere. Let me see. Oh, I didn't write it. Okay, but anyway, so the harsh conditions, it can be also reduced. But like I said, because of it's a very stable, unless you have a very, very severe conditions, it will not be reduced. That's why I showed the other ones in the room temperature, the normal pressure, only the one on the alkyl side will be reduced. And also sometimes benzylic position of the carbonic groups, but not benzene. You always stay the same unless you have a very, very high pressure and so on. But you can actually do it on the regular temperature, regular pressure, if you have a special catalyst, which is a rhodium on the carbon. And then the 25 Celsius degree, 1 atmosphere can do this because of the rhodium. So this is a kind of a special catalyst. So I'll stop here. Okay? So I'll try to